We're now ready to take a major step in our development of Lebesgue measure. In section 2.2, we'll define Lebesgue outer measure. Now, this is awfully close to actual Lebesgue measure. It's not precisely Lebesgue measure. What it is when it's nice, it's Lebesgue measure. There's a collection of sets that will restrict outer measure to nice measurable sets, they'll be called. And Lebesgue measure will be outer measure restricted to this sub-collection of sets. But what we're about to define is well on the road to Lebesgue measure, and we're seeking a measure M such that the measure of an interval equals its length for all intervals. And we'll show this holds for all intervals, open, closed, or whatever. The definition very much takes an inspiration from measuring intervals, open intervals, by their lengths. Okay, and this will also look a touch familiar if you think of it in terms of how we define measure zero. Definition of outer measure is, for any subset A of the real numbers, okay, so this outer measure thing is going to be defined on all subsets of the reals. Lebesgue measure won't. Let A be a subset of the reals, any subset of the reals, an element of the power set of the reals, if you like. And let I sub n represent a countable collection of bounded open intervals. So countable, bounded, open intervals, such that A is a subset of the union of those I sub n's. So the I sub n's form a cover of set A. It's an open cover of set A. We're not concerned with any compactness at the moment, at least, but it's an open cover with not just any old open sets, but bounded open intervals. So a countable collection of bounded open intervals. The outer measure of set A is defined to be M star of A. Star indicates outer measure, defined as an nth of a sum from n equals 1 to infinity of the lengths of those I sub n's. So we're summing up the lengths of the I sub n's, and the infimum is taken over all such collections I sub n. The infimum is taken over all such collections of open intervals covering set A. So we'll have various coverings of set A of this type, countable, bounded open intervals, and we'll sum up the lengths of those open intervals. The length of an interval, no problem. It's the right endpoint minus the left endpoint. By the way, that's the reason the word bounded is thrown in. I think they didn't have these as bounded intervals in earlier editions of the book. I like this approach a little better. Bounded intervals, the length is right endpoint minus left endpoint. So always finite. Of course, the sum could be infinite as far as we know. And measures, outer measures, can be infinite as well. But there's the definition of outer measure. If we were defining measure zero, then we could take this infimum and replace it with a for all epsilon greater than 0 and get the sum of these lengths to be less than epsilon. And that is how we define measure zero. So that measure zero stuff is consistent with this outer measure definition. First off, the outer measure of A is defined as an infimum. So the outer measure of A is defined for every set of real numbers. See, the real numbers, if a set of real numbers has a lower bound, then it has a greatest lower bound, an infimum. What we got here is a sum of a bunch of positive numbers. Lengths of intervals are always positive. An interval doesn't have length 0. Singletons don't count as intervals. Intervals have distinct endpoints. That's just what interval means. So the length of an interval is always positive. So if we're summing up a bunch of positive things, then the sum of those lengths will be positive. And when we take an infimum, we've got a set of real numbers here that's bounded below by 0, so that inf will exist. The lower bound on the set itself is 0, And when we take an infimum of the set of real numbers, it's guaranteed to exist by the axiom of completeness. So that's the reason M star is defined for all subsets of the reals. Okay, that's ultimately going to cause us a problem. It produces some undesirable occurrences. What it is outer measure is not countably additive, say. And we'll establish that. It'll take us a while to get through all the details, but remember, we had a wish list of 4 things for a measure. We wanted it to have the measure of an interval as its length. We'll prove outer measure does that in this section. We wanted translation invariance. Outer measure does that. We'll prove that in this section. We wanted part 3. Let's go to part 4. We wanted measure defined on the power set of the reals, and outer measure is that. But the third thing on our wish list from the introduction section 2.1 for this chapter, we wanted countable additivity. Outer measure doesn't give us that. So something's going to have to change. We've got to have countable additivity to do integration. What's going to change is we're not going to consider every subset of real numbers. We're going to restrict outer measure to a subcollection. And that's what will happen in the next 2 or 3 sections. Outer measure, the empty set is 0. If A is finite, a finite set, finite in cardinality, I have little problems. I don't mean finite in the sense of bounded. I mean finite in the sense of cardinality. Then the outer measure is 0, straightforward from the definition. If A is a subset of B, the outer measure of A is less than or equal to the outer measure of B. We call that monotonicity. We saw in section 2.1 that monotonicity was a property of certain measures. M prime was a measure we were considering then. That M prime was a measure that had the properties given to you by the exercises in section 2.1. We're going to consider 2 measures, outer measure and Lebesgue measure, in real analysis 1. Royden and Fitzpatrick claim monotonicity. And just a little brief comment. Let's give a proof of monotonicity for outer measure. This is not covered by that M prime result. M prime was monotone as well, as shown in one of the exercises. Yeah, that wasn't talking about outer measure. Outer measure means what we just defined. So let's go through a little proof of that. So the claim is, if A is a subset of B, then the outer measure of A is less than or equal to the outer measure of B. Okay, so tell you what, let A be a subset of B. Everything is a conversation about sets of real numbers. And we're going to consider the sets, let me call them X sub A and X sub B. These are the sets of which we're taking infima in the definition of outer measure. So we'll sum up the lengths of intervals, open intervals that are bounded, I sub n, and we're doing this such that these I sub n's, when unioned up, cover set A, and each I sub n is a bounded open interval. So in other words, we're covering set A with bounded open intervals, and then we're adding up their lengths. Vary the collection of open intervals that cover set A, changes the sum of their lengths probably, and ultimately we'll take an infimum of that to get the outer measure of A. Same thing for B. Cover it with open intervals, I sub n, bounded open intervals, I sub n, and sum up their lengths. Do that for various coverings. X sub A is all such sums of coverings of A. X sub B is the sum of all such lengths of intervals of coverings of set B. All right. To find an arbitrary element of X sub B, we need an arbitrary countable covering of B by bounded open intervals. Quick observation, hey, if you cover B, you're also covering A. And informally, that's what makes this tick. So it's just commented, to find an arbitrary element of X sub B, we need an arbitrary covering of B by bounded open intervals. So let this I sub n be such a thing, be a countable collection of bounded open intervals that covers B. B is a subset of the union of those bounded open intervals. Then, if you add up their lengths, that's an element of X sub B, because that's what set X sub B was sums of lengths of bounded open intervals whose union covers set B. It's a superset of set B. Yeah, but A is a subset of B, and we just said B is a subset of these intervals. So this same collection of intervals is also a covering of set A. Well, if it's a covering of set A, then the sums of the lengths is an element of X sub A, because that's what X sub A was. The sums of the lengths of bounded open intervals such that the union of those bounded open intervals, right here, covers set A. And this one does. So every element of X sub B, we just took an arbitrary element of X sub B, is an element of X sub A. We just showed this is an X sub A. That is, everything in X sub B is in X sub A, so X sub B is a subset of X sub A. A property of infima from your senior level analysis class is, if X sub B is a subset of X sub A, then the infima of X sub A is less than or equal, infimum of X sub A is less than or equal to the infimum of X sub B. And the supremum of X sub A is greater than or equal to the supremum of X sub B. It's in the correct order here. It looks odd because we got the subset inclusion. You're telling me the bigger set has smaller values in it? Yeah, that should make sense. There's more stuff in set A. So, okay, well, set A maybe includes some stuff that's smaller than the stuff in set B. And that's why the infima satisfy these properties, you know, just between you and me informally. But a property of infimum as applied to one set being a subset of another. And the inf of A, that is the outer measure of A, the inf of B, that is the outer measure of B, and there's our conclusion. Outer measure of A is less than or equal to outer measure of B. Outer measure of A is less than or equal to outer measure of B. Back to the notes. Okay, so useful. We know outer measure is monotone. Monotonicity is a useful property of measures. Royden and Fitzpatrick, I mean, they use monotonicity a lot. They didn't call particular attention to this. That's why I inserted this as an extra little lemma. We'll use monotonicity a fair amount in what we do. The following result shows that we're on the right track for the condition of outer measure of an interval equals the length of an interval. So we're about to establish that. Quick little comment. It's understood that the length of an unbounded interval is infinity when we encounter unbounded intervals. And proposition 2.1, really the first measure theory result in the book, says the outer measure of an interval is its length. Well, that was part one of our wish list of properties of a measure. We wanted the measure of an interval to be its length. Outer measure satisfies that. Let's prove it. Okay, outer measure of an interval is its length. We're going to go through this and establish it, and I think we do this in 3 steps. First, consider closed and bounded intervals. All right, so take an interval of the form AB, closed interval of the form AB. That's compact set, and we're covering these sets with open intervals. They're open covers. Okay, compact sets, that's going to give us some finite subcover stuff. So that's why we're starting with sort of a base case of bounded closed intervals. All right, let's get some wiggle room. Let epsilon be greater than 0. Consider the single open interval a minus epsilon over 2 to b plus epsilon over 2. Okay, that goes a little bit less than a and a little bit bigger than b. So that covers the closed interval from A to B. And the length of that interval, well, it's just the difference of the endpoints. It's b minus a plus epsilon. That's when we did the epsilon over 2. Epsilon's arbitrary, so we just showed that this interval can be covered with a countable collection of bounded open intervals, well, with one bounded open interval. The sum of whose lengths, the length of the single interval, is b minus a plus epsilon. Epsilon was arbitrary. We can make it as small as we like, telling us that that upper bound on the outer measure of that interval is b minus a, which is actually the length of the interval. Remember, we're trying to show the outer measure equals the length. This argument here with the arbitrary epsilon tells us we've got outer measure is less than or equal to length of the interval. We need to reverse that inequality. Okay, a standard epsilon argument based on the definition of an outer measure to show half of the desired equality and in the setting of closed and bounded interval AB. All right, so we need to reverse that inequality. Here comes Heine-Borel. Okay, next cover I sub n. Let the I sub n's be a covering of the closed and bounded interval AB by bounded open intervals, the kind of thing you cover a set with when speaking of outer measure. By the Heine-Borel theorem, there exists a finite collection of these I sub n's, a finite subset A of the I sub n's, consisting of the I sub n's covering set AB. You're right. AB is a compact set. We've covered it with open sets. They're open intervals. Heine-Borel says it has a finite subcover. So there's a finite number of the I sub n's that also cover AB. Heine-Borel says closed and bounded sets of real numbers are compact sets. Compact says every open cover has a finite subcover. So there's all the details. So we transition from the infinite to the finite, which is the real reason compact sets are interesting. Heine-Borel's nothing to do with interests in compact sets. The interesting thing is the definition of compact set. Open covers have finite subcovers. Heine-Borel just makes it easy to recognize compact sets of real numbers again. Okay, so we got a finite collection of these I sub n's. What we're going to do is we're going to cover A, and then we'll see that there's some overlap with another interval that covers a little bit more, and another interval that covers a little bit more, and eventually we must reach point B. The finiteness is necessary for that. More specifically, A, the left-hand endpoint of this interval, it's got to be in one of these I sub n's, denoted I sub 1. So say A is in I sub 1, one of those bounded open intervals. Then I sub 1 is, say, of the form A sub 1 to B sub 1. A is somewhere in there. Well, either this single interval covers the whole interval A to B, or B1, the right-hand endpoint here, is less than or equal to B, and you haven't covered the whole thing yet. If you haven't covered the whole of closed and bounded interval AB with a single open interval, that is, if B1 is less than or equal to B, so you haven't got to B yet, then there must be an open interval containing B1. B1 is an interval, is an element of one of those open intervals. Let's call it I sub 2. Let the endpoints be A sub 2, B sub 2. Well, either this thing contains endpoint B or it doesn't. If it doesn't, then B sub 2 is an element of this closed and bounded interval and has to be in an I sub 3, and so forth. So what we're doing is plopping these intervals down. Eventually, we have to get to point B because it was a covering of the whole thing. And there's only a finite number of these. So we've got the intervals of this form where A sub I is less than B sub I minus 1 is less than B sub I. And what that means is B1 is somewhere in this little interval. So the second interval overlaps with the first interval. The third interval overlaps with the second interval, and so forth. So there's these little overlaps in the intervals. Okay, and there's a finite number of those intervals. That's how we were able to lay them out one after another and know that you actually covered the whole thing. You reached right-hand endpoint B. If we add up the lengths of all of the I sub n's, these I sub n's that we started with that we were covering of the interval AB, well, it's greater than or equal to just this bunch of them that we kept, the I sub 1 through I sub k. that we've introduced here. So greater than or equal to, for all I know, that was all of them in this countable collection. Countable means finite or infinite and countable, countably infinite. So the word countable does encompass finite as well. For all I know, those could be the same, so I do get an or equals to there. And if you sum up the lengths of the intervals and the symbols introduced, that's easy enough. That's B1 minus A1, so the length of the first one, B2 minus A2, the length of the second one, and so forth. So we get a sum from I equals 1 to K, right-hand endpoint minus left-hand endpoint, over these little subintervals. Now, we knew this type of relationship here. We created these in such a way that there was that type of overlap. So if I write all these out from I equals 1 to K, I've actually written them out from 1 to K, right to left, but I got my reasons. Here's the B sub K minus A sub K. Here's the subscripts of K minus 1 and so forth, all added up down to 1. Let me bracket these off as follows. Let's collect together the A sub K and the B sub K minus 1. So we need to put a negative sign out there to keep the signs balanced. You would agree the first three terms here is the same as the first three terms in the previous line. I mention that because we know from this condition here that A sub I is less than B sub I minus 1. That's exactly when I equals K. That's what we have here. We've got A sub K minus B sub K minus 1. That's negative. Take this to the other side. We get A sub I minus B sub I minus 1 is less than 0. Negative. These are all negative. This is negative. And we get a similar pattern throughout, and all of those are negative. So we're subtracting negative things. All right, well, if we're subtracting negative things, we're actually adding positive things. Let's drop all these positive terms and get something smaller. So we're going to keep the B sub K, keep the minus A sub 1, and drop all these positive things in between. Introducing, it's buried at the bottom, introducing B sub K minus A sub 1. This is greater than B sub K minus A sub 1. It's visible down there or not. There's a greater than B sub K minus A sub 1. Next slide. Oops. Is exactly what we had from the previous slide. So we've got the sum of the lengths of the intervals is greater than B sub K minus A sub 1. We had A sub 1 is less than A. A was in that first open interval. A sub 1 was the left-hand endpoint. B sub K is greater than B. B was an element of that Kth subinterval, and B sub K was the right-hand endpoint. So when we covered the closed and bounded interval from A to B, it slopped over the left-hand side a little bit, and it slopped over the right-hand side a little bit. It had to. You were covering a closed and bounded interval with open intervals. So we had to have that intermediate overlap, and we had to have it slopping over the sides. We've thrown away the overlap when we got this greater than, and now we're fixing to throw away those stuff that slops over the side and observe, hey, A1 is less than A, B sub K is less than B. That implies B sub K minus A1 is greater than B minus A. Convince yourself of that. It's straightforward arithmetic. So B sub K minus A sub 1 is strictly greater than B minus A as well. You manipulate these two to convince yourself of that. And therefore, the sum of the lengths of these intervals is greater than B minus A. Let's see, we were talking about, what was it, outer measure? We want to take an infimum over all such I sub n's, all countable collections of set interval AB by open bounded intervals I sub n. So we've taken infimum to get the outer measure. If we know each of the terms in that set is greater than B minus A, then we know the nth of that set, which is the outer measure, is greater than or equal to B minus A. So we've got the nth to be greater than or equal to B minus A. First part upstairs, we had the outer measure to be less than or equal to B minus A. Okay, outer measure is greater than or equal to B minus A, less than or equal to B minus A. It must equal B minus A, and that's the length of the interval. All right, so what we've got here is that the outer measure of a closed and bounded interval is the length of the closed and bounded interval. So the result holds, showing the outer measure of an interval is its length. The result holds for closed and bounded intervals. That ain't all intervals. All right, well, consider an arbitrary interval. There we go. Consider an arbitrary bounded interval I. All right. Well, we already know good things relative to what we're trying to show. We know good things about closed and bounded intervals. So, I'll tell you what, give me a little wiggle room. Let epsilon be greater than 0. We can find a closed interval inside this arbitrary bounded interval, closed interval, let's call it J, a subset of I, such that the length of J is greater than the length of I minus epsilon. You gave me some wiggle room. I had some particular open interval. I went in a little bit and closed off. Maybe I went in epsilon over 2 and closed off, or epsilon over 3 and closed off. So I can, for a bounded interval, go inside that interval. I don't know if that interval includes endpoints or what. Well, if I go inside a little bit, then I can include endpoints. So we can go inside the bounded interval I with a closed interval J, closed and bounded interval J, and make the length of J close to, but less than, the length of I. The epsilon is the close to, the minus is less than. So length of I minus epsilon is less than the length of J. Close to and less than is the idea. We've got the outer measure of I, less than or equal to the outer measure of I closure. That's monotonicity. The bar means closure this time. Okay, so what's the difference in I and I closure? I is a bounded interval. So I closure is that bounded interval along with its endpoints. Maybe it already included its endpoints, maybe it didn't. It was an arbitrary bounded interval, I don't know. But I do know I is a subset of I closure. The only difference in those sets possibly is the 2 endpoints of the interval. But monotonicity allows us to say the outer measure of I is less than or equal to the outer measure of I bar. We establish monotonicity in the lemma. So when we say the length of I minus epsilon is less than the length of J, this property here, we know the length of J equals the outer measure of J. Why is that? Because J is a closed and bounded interval. And we know closed and bounded intervals, like this one, have outer measures that equal their length. So the length of J is the outer measure of J. We know J is a subset of I. Well, if J is a subset of I, monotonicity gives us a less than or equal to. Outer measure of J is less than or equal to the outer measure of I, monotonicity. We know the outer measure of I is less than or equal to the outer measure of I closure. Less than or equal to the outer measure of I closure. Monotonicity again. Told you monotonicity was useful. Hey, what kind of interval is I closure? Bounded and closed. We close it off. So the outer measure of I closure equals the length of I closure, because I closure is a closed and bounded interval. And we know for closed and bounded intervals, the outer measure and the length are the same by part 1. So the outer measure of I closure is the same as the length of I closure. The length of I closure equals the length of I. How do you find the length of a bounded interval? You take the difference of the endpoints. Well, I closure and I, they got the same length. I mean, right-hand endpoint minus left-hand endpoint. They got the same endpoints. I closure includes those endpoints. Maybe I doesn't include those endpoints, but that doesn't affect the length of the interval. So we've established length of I minus epsilon is strictly less than outer measure of I, which in turn is less than outer measure of I, which is in turn less than or equal to the length of I. So we've established this kind of thing here. Remember where we're going. We're trying to show for interval I, the outer measure of I equals the length. All right, well, we've got the length of I minus epsilon, outer measure of I, that's some fixed number, length of I, that's some fixed number. We've got the measure sandwiched between the length of I and the length of I minus epsilon. And epsilon can be made little, so think of it like a sandwich theorem. I want to say as epsilon approaches 0. Well, epsilon is an arbitrary positive number and can be made arbitrarily small. Since the outer measure of I is sandwiched between L of I and L of I minus epsilon, when epsilon gets little, of course, this left-hand thing and right-hand thing get close to each other, sandwich theorem style. And so we can reach the conclusion that the length of I equals the outer measure of I. So using closed and bounded intervals, we've established the length of an arbitrary bounded interval equals the outer measure of that interval. So the only constraint we have is that was imposed in step 2 was bounded interval. So all bounded intervals satisfy the theorem. That just leaves unbounded intervals. Well, easy enough. If I is an unbounded interval, then its length is going to be infinite, and so is its outer measure. We'll establish that by packing it with closed and bounded intervals. If I is an unbounded interval, then give me any natural number. There's a closed interval, J, a subset of I, where the length of J equals N. It's an unbounded interval. I can find intervals of length N that are subsets of that interval, and I can make them closed. I got room to move around, a lot of room in an unbounded interval. In that case, we've got J as a subset of I. By the way, we made J closed. It's bounded because its length is N. So J is closed and bounded. I can use part 1 on it. I do need the boundedness even if I use part 2, but we did make it closed and we're using part 1. We know the outer measure of J and the length of J are the same. It's a closed and bounded interval. We showed that in part 1. We've got J as a subset of I. So the outer measure of I is greater than or equal to the outer measure of J. That's monotonicity. So we got monotonicity there. Part 1 links the outer measure of J to the length of J. And we made J have length N by construction. That is, we've shown that the outer measure of I is greater than or equal to N, and N was an arbitrary natural number. Since N can be anything, the only way this condition can be satisfied is if the outer measure of I is infinite. And we said we've got an unbounded interval. Unbounded intervals have infinite lengths as well. So the outer measure equals the length. So the outer measure of an interval is its length. Excellent. On our wish list of 4 things for a measure, this was thing number 1. Remember, we're going to ultimately set up integration. Riemann does that by taking little delta x's, delta x sub i's, little lengths of intervals, and he makes rectangles with certain heights. But he measures the bases of those rectangles with the lengths of little subintervals. We're going to replace the length of a subinterval with a measure of a set. When those sets are intervals, we're going to get the same thing because the measure of an interval is its length. So that's why this is important with an eye towards integration.